Cool. So, I mean, mostly I was just showing some videos of robots doing things that are on our blogs. So if you want to see them, they're there. Nothing too new. But yeah, so essentially, because we want to be able to do these high frequency controls, we look to things like flow matching and diffusion, and in this case, attach a flow matching action expert and train that with a VLM backbone. Unfortunately, this converges really slowly. Essentially, the gradients out of this action expert are not great for the VLM's convergence. It doesn't necessarily lead to a really phenomenal representation space, and it takes over 1 million steps to converge. I think it was 1.2 million steps for Pi Zero. And eventually it does get to some decent performance, but this like time is just too slow. You're essentially like corrupting the initial network and not using your backbone very well. So FAST proposed a way to sort of break the fact that these high frequency controls are so repetitive with a discrete cosine transform, where you just represent your actions instead as a series of cosines. And this actually works really well for learning. So this ends up being like an order of magnitude faster to convergence, but the inference is very slow. So you have to autoregress, I think, 300 tokens. This takes like a little under a second for certain robots. And so you have this like frequent pause as you move. And I'll show some videos of what this looks like. But this convergence is really nice. So it's kind of natural to say, okay, how can we get best of these? So if you add in just joint training, so have some like loss across each of them with the action expert and with this discrete cosine transform, at first it learns really quickly, but then we find that it overfits pretty quickly, or it overfits after 100,000 steps and doesn't asymptote to really high performance. So what we wanted to do was come up with some way to sort of combine these, but actually get the best of each. And so we introduced this knowledge installation idea, which is essentially a way to maintain the initial knowledge of the VLM. Ideally, we get better generalization out of this and better performance and better training performance by just adding in this stop gradient. So earlier we had gradients from the action expert that we know kind of corrupt the VLM backbone. Why don't we just not let them pass through, but still train the action expert? And indeed, this converges as well as Pi Zero Fast, but we actually get inference speeds that are on par with Pi Zero. So and what this looks like is both of Pi Zero and Pi 0.5 with knowledge installation have under 100 milliseconds inference speed, but Pi Zero Fast is much slower. But we still inherit the training speed benefits. We still inherit a lot of the knowledge and generalization from that VLM backbone. And as I was saying, what it looks like is on the right, we have this with knowledge installation where we have this action expert, and you can see how much faster the shirt folds are or busing a table is. Even these are like a little slow. I think there's times where we have much faster policies. But on the left side, you have fast. And ironically, fast's inference is so slow that you have these huge breaks in shirt folding, though it does eventually achieve it. It takes a while to get out of the home position here in this UR5 example. Essentially, it just can be, the inference speed is slow, and then the behavior when there's a lot of multimodality can often be to slow things down. Now, in performance, we see specifically that the knowledge installation approach works very well. We get very high performance. You can see the task here of just opening a drawer and then putting a bunch of objects in there. It outperforms each of these other ones. Like a frozen backbone is a really easy way to maintain this performance that just like does not work very well. The joint training still works reasonably, just not as well as if you have this stop gradient. And as I said, it sort of asymptotes. And then in speed, like time to complete the task, this is just on successful episodes. It also moves much faster, so the robot is just smoother overall compared to other approaches. And then in language following, where one of the things with knowledge installation is basically maintaining that initial knowledge of the VLA. We see that in distribution, joint training with basically joint training and not joint training works about the same. But the second you go out of distribution, and especially if you don't have VLM data, so it's these bars down here, you basically lose performance entirely. So you need something that maintains the initial VLM's performance. Otherwise, this action expert essentially destroys the overall performance. And then if we go back and look at like Pi Zero and Pi Zero Fast, the language following abilities just weren't quite as good because they're not getting as much out of this VLM backbone. And yeah, specifically out of distribution, I think we see this trend. So the next half of this, though, is data, which probably arguably has more impact on the overall performance. And so to give kind of a brief history of where we are as physical intelligence, we started, there's open source data sets like OpenX embodiment. And then around 6 months in, we had about 10,000 hours, which is just over a year of data. We had tasks like building a box, but also folding a shirt, doing laundry, just kind of a number. We really wanted variation over these tasks. So there were about 100 of them, a fair amount of environments, but the environments were really just like in our lab setting. So the next bit was about, can we then scale this up to really diverse environments and basically see, can we get generalization? So we started collecting in a lot of Airbnbs in a lot of diverse environments. So around 100 environments with mobile manipulators so that we can get to more complex, really long horizon tasks. And then started collecting, order 500 tasks, I think. Now, the most, I think, important finding with this is that essentially, as we scale the number of locations, performance of an unseen environment improves. And what wasn't clear is like when these lines would intersect. So in the green line, we have just in-domain data, and there's like a ton of in-domain data. We actually like balance the two. And then the yellow line is as we increase the number of locations that we're training from. And you see that at about 100 environments, we start to at least equal performance. And maybe if we continue this to the right, we're going to pass the performance. But I think some of like the really important stuff is seeing how much pre-training matters in this. So training on a huge diversity of data that's not just this mobile data. And so that's these numbers over here on the right. So even in domain, without this pre-training, the performance goes from like low 80% to around 40%. Now, if you add in these other data sets, these 100 environments that are about the same performance and don't have pre-training, you basically get zero performance. So this pre-training was really necessary to be able to get this generalization to a new environment. And again, like all the yellow line is just an unseen environment, essentially some new Airbnb that we hadn't seen before, and seeing whether how the performance is. So other things we looked at were the types of data that goes into this mixture. And so this is like the bread and butter data. The mobile manipulator is about 400 hours of this, but there's a lot more of web data. So VQA, object recognition, bounding boxes, also some cross-embodiment data. So this is mostly collected within our lab setting, not a lot of visual diversity, but a lot of diversity of the type of robot. And then also a bunch of multi-environment data where it's just single arms that we essentially like walk around the Airbnb and clip to stuff and then collect data with. And you can see one example here. But essentially, this is going to see a lot of environments and a lot of visual diversity and have a fairly similar embodiment, at least from the arm perspective of the mobile manipulator, but is very easy to go and collect. And so first, zooming in on web data, I think we see some performance gains. It definitely helps. I think the more out of distribution you go, the more it helps. But in distribution, it doesn't make a big difference. And then overall, it's a kind of subtle drop. But these other types of data are really, really important. So the cross-embodiment data, the second you get rid of it, you lose 30% performance, language following goes down. Multi-environment also has a huge impact. So having seen a diversity of environments, of ways in which the world can be set up, and if you remove both of them, you get down to 40%, so about half performance, which is basically to the level where it really like doesn't feel like it's working. You don't see it, really doing what you expect. And very similar trends on language following, particularly when you go out of distribution. I think one lesson that we really found here is the things that you see in distribution give you some signal, but really until you go out of distribution, until you're testing in novel environments with novel objects, you often don't know what these kind of changes are going to make. So particularly multi-environment data makes a big difference the second you go out of distribution. The other thing we looked at was high-level performance. So the way the architecture works is you have this high-level model that's breaking down a task like clean up the kitchen into a bunch of sub-steps for the low-level model. And I want to highlight just a few things that I think were like very surprising here. So as we were working on this and improving performance, we essentially were starting with this baseline, this green one with no high level, there's no high level, and then you would add in high level and you would jump to this yellow performance. When it came time for the final paper, we had added in this co-training between the two, and suddenly we go and check how much the high level is helping, and the performance the delta has dropped a lot. And what we realized is by just implicitly training with the high level data, even if you don't use it at runtime, you got this pretty big boost. And this was very repeatable. We're a little bit surprised that it was doing so well. We also held that part out to see, does this matter as much as we expect, because it wasn't something we were expecting to see, but it makes a really big difference. So there's some implicit representation being learned about breaking it down into the next step and kind of committing to it. The other things that really matter, having some instruction data where you go around and actually show it how to work with the low-level policy. So the low level makes mistakes that maybe a human wouldn't make, so you can end up with a much more robust policy. Web data helps more with the high-level policy than it necessarily does with the low level. And then for each of these, we end up actually beating the human high level. And I think there's a few things here. These are on maybe like 2-minute long tasks. I think human high level starts to do really well when you get past that. There's also sort of this dichotomy where the high level model is kind of perfectly mated with the low level model as it is. So it means it like never makes a typo or speaks in a different way, which I think adds a little bit of robustness. It also is being queried every 2 seconds, whereas a human maybe isn't giving updates at that frequency. And then there's a sort of characteristic where if a person asks the robot to do something and it makes a mistake, the person may continue to insist that the robot change what it does, even if both ways would be a way to sort of further the task. And I think this kind of like fighting the robot at times versus the high level model will just switch and say, as long as it's making progress towards the task, I'm okay to switch to another object. I think that actually helps performance in the long run. So what this ends up being, and this is kind of the full system together, if Laura just wants to say like clean the bedroom, we can basically, in this unseen environment, we can break it down into a series of substeps that the low-level model can achieve. It can do pretty dexterous things like making this bed. And I think like making the bed is really complicated because there's this, when is the bed made? How do you manipulate a sheet is actually very difficult. There's obviously some navigation involved, so I think we can like push this much farther. But this is sort of where we end up when we put all these recipes together. So just to like quickly highlight things that really don't work that well right now. So first, really long horizon tasks sometimes don't work. Essentially, if you want to like put together these substeps, so maybe making a bed and cleaning up a room, a lot of times the model doesn't know when it's completely done. And you'll see on this far right version, it essentially goes home a little too early, and just once it's in that home position, it's stopped. And so being able to track overall long horizon progress and know when you're done, especially if you get out of distribution and make a mistake, I think is still a pretty big problem. The other thing is, I think the policies are still much slower than what like our human demonstrations are, and certainly what a human can do. And they make simple mistakes like here, where it tries to close the drawer with a oven mitt. Even though there's a fair amount of data of this, and it might work 80, 90, 95%, but it still makes simple mistakes. Similarly, leaving this pillow in the middle image. Great, and I think that's it. So if there's any questions or.
Thanks for the nice talk and very interesting about the gradient corruption problem in the VLA models. I want more of your comment on the how knowledge insulation really helps. Is it like you are like in transfer learning, you stop the gradient and then retrain it, something like this way, or how it works in the real sense that because vision language model, especially in VLA, action things is known to corrupt the vision language modality quite highly. So how noise insulation in real time works in your case?
So the question is basically why, like, sorry, can you like rephrase it?
So it's like, what is inside the knowledge insulation which you are doing, which helps VLA that gradients are not corrupted?
I see. So essentially, like, what are we preserving of the VLM that? I mean, I think in general, because they've been pre-trained auto-regressively with cross-entropy, you have this different losses gradients coming through. And I think that just ends up pushing it to, you basically aren't using the pre-training nearly as much when you do this. It also is going to be a very kind of orthogonal gradient, to kind of abuse the term, that is going to reduce the initial knowledge. Like, you're basically destroying everything that was there. Whereas I think using the cross entropy of DCT tokens doesn't seem to do this, that this gradient is much more aligned with what the VLM already knows.
Okay, so is it kind of like a PPO where it's for the regular, like in, you don't want to go quite far from your initial knowledge, so something in this direction?
Yeah, I think there's probably something like this, that it's essentially regularizing it to stay near where it initially was.
Okay, got it.
Yeah.
Very interesting. Thank you.
Thank you for your presentation. I really enjoyed it. I had a question about if there's any benefit for integrating like symbolic reasoning to kind of fix those issues that you kind of highlighted later in your presentation. Like some people do like predicate classification, things like that. Is that something physical intelligence is looking into?
So not explicitly with symbolic reasoning. I guess the closest we've done, we did try to get really long horizon tasks to basically track which tasks that you're on. So let's say that we can break down cleaning up a bedroom into making the bed, putting things away in a nightstand, and throwing away trash. If you know that these are going to be the sub steps that are still maybe minute plus long, we can basically say which one am I in right now, and then detect whether I succeeded at something, and then move on to the next one. And this works for a bit, but what ends up happening is if you get anywhere out of distribution, or maybe you complete one task and you back up and now you're in free space, you end up predicting that you're done with each of the next ones. And so I think this kind of transition is both really like brittle for the overall algorithm, and then kind of hard to learn at the high enough degree to overcome that brittleness is just not robust. But I think like it definitely helped. It just didn't work super well because of this.
Got it. Thank you.